Hey Kata, wanna talk about Mscripten?
Wait, should we check the connection? I've missed some letters.
Nope, that's the actual name. We're going to run some C++ in the browser, but let's start from the beginning. Okay, before talking about Mscripten, we need to talk about WebAssembly.
Yeah, it's a binary instruction format which is designed to be portable and can be used to write application for the web. It can be used both on clients, aka in a browser, and on the server, for example, in Node.js.
Correct. The really cool property of WebAssembly is that it's so low level and so similar to classic assembly that it can be
Yeah.
integrated as yet another target architecture in existing compilers for other languages.
So, what about Mscripten?
Getting there. So Mscripten is a compiler toolchain which uses LLVM, aka the base on which Clang is built, to compile C and C++ to WebAssembly. It also provides a series of libraries to ease the communication between JavaScript and C++. For example, it exposes WebGL as OpenGL. It provides a virtual file system, and so on and so forth.
Boring. Can we show something to our friends now? Pretty please.
Okay. For simplicity, we're going to use Bazel. I know you're all caught up, but you can watch the previous episode if you need a refresher on what Bazel is and how to use it. Okay, so this is a super simple example. So we are just exposing with an extern C, which is just a way of exposing functions in your binary. We're just exposing an add function. We're using this macro from mscripten.h to get this macro, which is used by mscripten to properly expose the function in the final binary. And this is a really simple function. We're adding two numbers. We get two doubles, and we're adding them and returning the value. Uh, what we need, and well, as you know, you need to add your
Oh,
dependency.
yeah, look familiar.
Yeah, so in order for Bazel to know where to get the stuff, we are adding EMSDK, which is the current
Okay.
integration dependency in Bazel that uses Mscripten, and our good old rules CC that we used in the previous episode. So in our build
Okay.
file, we are including these two rules, and specifically we need a CC binary rule which defines a C++ binary. In this case, is a really simple one with just one file, and then we have the WASM CC binary, which takes a CC binary and converts it to WASM. So at that point, we can go and just Bazel
Oh, yeah.
build our target. It's there. It built,
Okay.
and now we can go spawn up our node. We can require our target as if it was a normal JavaScript file. This already Mscripten already provides for you what is called a loader. So this file already goes and talks with the proper libraries in the JavaScript VM to load, compile, and so on the binary, and just loads it and provides it to you. So now we have this M, which is our module, and you can see there are a couple of files that are exposed automatically by Mscripten, but what we care about is this underscore add, which is the function that we actually expose. So we can go and say m.add 2 and 3, and you guess it's 5.
Strange. It worked like a charm. But again, boring. But I think that this is going to be fun. Do you know zlib, the super famous library to handle compression and the compression of data?
Yes, why?
While Node.js exports the native version directly, in the browser, various libraries found ways to implement it in JavaScript in an efficient way, in various efficient ways. For example, did you know Paco?
What is it?
This is a library which also provides a benchmark to test different implementation against each other and against the native zlib too, the one that is integrated inside of Node.js. I'm wondering what happens if we compile zlib with mscript, for example.
Well, let's do it.
Okay.
Okay, so here we are. This is a really rough implementation.
Nice.
Yeah. So what we're gonna do is that we're gonna process. This is an implementation detail of zlib. It works in chunks. So we're gonna buffer chunks of 16K, and so this is just here to allow us to prepare our chunks together and then compact them at the end. So we just go in, we initialize when we are deflating, we are initializing our stream operation. We set it up with the input. So you see that this function is taking a void star in, which is the input buffer. It's just a buffer of bytes, and it takes the size of this buffer and the compression level. I mean, zlib supports different compression levels, and then we return an output buffer. So again, we we initialize the streaming process. We say that the available input is the whole size, and we say that the first byte of the input is the next that needs to be processed. Then we have our list of chunks, and for now the total size is 0. And then we keep on going until there is input to process. When there is no more input to process, we stop. And then what we do here is that we create a new chunk. We set it as output. So we say how much space is available in that chunk, and we give it the address of the first byte. And then we continue the stream. This goes through, and at that point, we just store how much of that chunk or that chunk buffer was used, and we keep it up to date. And we go through until there is no more input to process. And in the end, we allocate a contiguous output buffer, and we are doing this trick because, well, this is C++, or specifically we're using the C linking format. So we are limited to basic simple types. So at this point, we are using a buffer that also contains its length as the first element, as an integer. So we copy the length in the first position, and then we go and we just copy all the chunks together into this output buffer, and we finish the processing. The inflate is the exact same thing, just that I'm initializing the inflate instead of the deflate. I'm processing inflate instead of deflate, and at the end I finished the inflate instead of the deflate. So it's the same
more easy
exact
than the first
thing.
one.
Yeah. And
once you have set up all things in the correct way,
the next important thing to do is that we need to go in here. Well, we have updated our build rules, but specifically we need to tell the compiler that we need to keep malloc and free available, because we need to be able to allocate these buffers. We want to expose heap u8, and then I'm talking about what that means in a second. And then we're saying that we want the loader to perform compilation synchronously, because we are going to use it for now in Node, so we don't want to wait for the compilation. So then let's go into the JavaScript side. And again, inflate and deflate are the same thing. You just slightly change.
What a wall of JavaScript.
Yeah. So what's happening here is that we get our incoming data, which is going to be uint8 typed array and the compression level. So an important thing is that WebAssembly cannot access memory that is owned by the JavaScript VM. It can only access its own memory, and this memory, in this case, we are exposing the entire memory available to C++ as a typed array of bytes. So this is effectively a view inside the whole memory space available to C++. So effectively what we're doing is that we are allocating a buffer. We're just calling the good old C malloc. And then we go and we say that given that this is the whole space, well, the pointer to this buffer is effectively the index of the first element of the buffer.
Yeah.
So what we say is that we want to get the chunk of memory that is equivalent to the buffer that we just allocated. So from wrapper data up to wrapper data plus length. And we are allocating, we are setting as a value to this buffer the content of the input. So effectively, it's a really convoluted way to say that we are copying the input data into memory that is accessible from C++. Then,
yeah, so the magic is also here with the WebAssembly because we have the malloc exposed directly from the C.
Exactly. So, and I mean, there are other ways. There are available libraries that you do this, but we are going with pure Emscripten right now. So
we keep it easy for now.
Yeah. So now that we have our buffer, we are calling our function that we have exposed from C++, and we get our output. And then now that we don't need the input anymore, we're just calling free. We're releasing it. And then
right.
This is another interesting way of doing this. So we are effectively saying, hey, I want to take a look at the output buffer as if it were integers. And then I want the first one, as you remember, we said that the first part of the buffer is an integer, so int32. So we just go and read it, and that's the length of the buffer. So we allocate a buffer, a uint8 buffer, where to copy the data, and then we go here and we just copy the actual data out, and we store it in deflated, and then we go and we release the memory that was allocated natively inside wrap deflate. Again, this is a really convoluted way to say we are copying the data out of the buffer that that C++ created. I mean, in this case, we're doing it for technical reasons that we'll see later, but one could potentially avoid this if it just needs it right away. And and then we go in.
And let me guess one thing. Inflate is the same.
Exactly the same. Exactly the same thing, and I'm just calling wrapped inflate in the middle. Okay, so we can go. We can build it.
Oh, yeah.
Yeah, and then let's go to Paco. So we're not going into details of how Paco works and everything, but if you want to add the benchmark in the available benchmarks of Paco, you just build these two folders, one for deflate and one for inflate. So we just created a deflate macaroni, which is our implementation. And this is doing nothing more than just loading the library that you just saw and calling deflate. And I mean, this is exactly the same as the Paco implementation. In their case, they are loading the Paco implementation and calling it. So we're doing the same thing with our, and inflate, you guessed it, same thing. We're going and we are calling our inflate version there. So what we can do is that we can go here and trigger a benchmark.
Oh,
it's gonna take a while.
It is running.
Yeah, it's gonna take a while.
I suppose. We have time to wait?
Yes.
Okay. Well, we ran it multiple times and That seems anticlimactic. I was hoping it would have been faster.
Well, do you remember that this is C++?
Yes, so?
Well, what if I told you we have been running in fast build mode until now? Let's build it in optimize mode.
Do it.
Okay.
I want to see it.
Now it's in optimize mode and
Last hope.
time for another benchmark.
Go with it. We have to wait again.
And boom! As expected, it is not as fast as the native one, but is significantly faster than the end optimized.
Yeah, but what if we...
Kata. I know, but it's time to go for today. I'm sorry.
That is so sad. I was starting to have fun.
Yeah, we could have another episode on which we talk a bit more about the available utilities, how to write bindings, and all the best bells and whistles of Emscripten.
That will be fun. Let them decide.
Yeah, folks, leave a comment below if you're interested in this topic.
See you next time, folks.